So an induction motor, also commonly known as asynchronous motor, and it is also known as an AC electric motor. So here the meaning of asynchronous motor is that the induction motors do not run at synchronous speed. We know what is synchronous speed, that is given by 120 F by P. So the induction motor always runs at a speed which is less than synchronous speed. That is why they are also called as asynchronous motors. And they are widely used in industries, commercial areas as well as in domestic applications. So 90% of the industrial motors are of induction type. And a great scientist, Nikola Tesla, is the inventor of this wonderful machine. A very important, or I would say a very interesting fact about an induction motor is that induction motors are also called as rotating transformers. Why they are called as rotating transformers? See, in case of transformers, we know that how the EMF is induced. They are induced through the principle of mutual induction, or I would say just induction principle. So in case of induction motor also, since we have stator, that is the stationary part, and we have rotor, which is the rotating part of the induction motor. So here also the voltage, or I would say the current that are induced in the rotor is through induction principle. Here we do not give any excitation to the rotor or to the field winding. Here the voltage or the current which is required in order to produce the torque is directly induced from the stator winding by the principle of induction. So that is why the induction motors are also called as rotating transformer, since they are rotating in nature.
Now let's construct a three-phase induction motor using these elements. First, wound all the conducting wires on the stator core, all around it, to form three different parts of the coil that behave as three-phase winding. Then attach 4 outlet wires to these 3 parts of the coil to connect them to a three-phase supply. Then place this stator core inside the frame to form a stator of the induction motor. Now insert the conducting rods in each slot of the motor core. Then weld the end rings on both sides of the rotor core to short circuit all the winding rods on the core. This forms the rotor of the induction motor. Now place this rotor inside the stator carefully, and then finally attach the 2 end belts to it to form a three-phase induction motor. Thus, we have constructed a three-phase induction motor.
In this video, we will go to learn different types of AC motors. Electric motors are basically 2 types, one DC motor and another AC motor. AC motor is 2 types, one synchronous motor and 2 asynchronous motor. Asynchronous or induction motor is also 2 types, single phase motor and 3-phase motor.
Explain the principle of operation of a three-phase induction motor. We know that when a three-phase supply consisting of 3 phases and a neutral wire is connected to a three-phase induction motor, its rotor starts rotating. Let's understand what makes the rotor rotate. When a three-phase AC supply is connected to the three-phase stator field windings, they start behaving like electromagnets and produce 3 independent alternating magnetic fluxes. The resultant of these fluxes is called the net flux. We see that its magnitude remains constant, but position keeps on changing with time in circular manner. Hence, net flux develops a rotating magnetic field in the stator, which causes relative motion between the net flux and the rotor. Since the magnetic flux linked with the rotor keeps on changing, a current starts flowing in the rotor winding. As per the Faraday's law of electromagnetic induction, the direction of this current is given by the Fleming's right-hand rule. We know that when a current-carrying conductor is placed in a magnetic field, it experiences a force. Similarly, when a current-carrying rotor is placed in the stator magnetic field, it experiences a force and starts rotating. The direction of rotation of the rotor is the same as that of the rotating magnetic field of the stator. We can say that a three-phase induction motor works on the principle of electromagnetic induction, where the relative motion between the flux and the rotor caused by the rotating magnetic field induces a current in the rotor, forcing it to rotate in the same direction. Related terms are
give connections to the motor as shown. Close the main switch to start the motor on no load. Observe the direction of rotation of the motor, say, looking from the left-hand side of the terminal box. You notice that the motor shaft is rotating in the clockwise direction. Measure the RPM with a tachometer. Open the switch. Interchange the connections of any two input supply terminals of the motor as shown. Start the motor once again. You can now see that the motor shaft is rotating in the anti-clockwise direction. You check the RPM again. You can see that the speed obtained is the same as in previous case. You have succeeded in reversing the direction of the motor. You have practically seen how to reverse the direction of rotation of a three-phase induction motor.
There are two types of AC motor. One is synchronous motor and second is asynchronous motor, induction motor. Three-phase induction motor is a self-starting motor. Motor have two main parts, one is stator and second is rotor. Speed of three-phase induction motor can be controlled from stator side and rotor side. The main method for controlling speed of induction motor are: one is by changing number of poles, second is by stator voltage control, third is by V by F control, and fourth is by rotor resistance control. By changing number of poles. This method is used for squirrel cage rotor motor only. The number of stator poles can be changed by three methods: one is multiple stator winding, and second is method of consequent poles, and third is pole amplitude modulation. We have Ns is equal to 120 F by P, where Ns is the synchronous speed, F is the frequency, P is the number of poles. So by changing the number of poles, synchronous speed changes. By stator voltage control, we have this formula. Torque is directly proportional to stator voltage. This method is very easy and cheap, but still used rarely. Because by decreasing the voltage, torque will reduce. But this will increase current in motor, which will heat the motor, which is not good, it causes losses. Also the torque is proportional to square of voltage, so large voltage change is required for changing torque. By V/F control, we have Ns is equal to 120 F by P, where Ns is the synchronous speed, F is the frequency, P is the number of poles. Also, V is equal to 4.44 phi FTK, which means phi is directly proportional to V by F, where V is the voltage, phi is the flux, F is the frequency, T is number of turns per phase, K is the winding constant. If we increase the frequency, F, flux, phi will decrease because they are inversely proportional, and if we increase the voltage, V, flux, phi will increase because they are directly proportional. In this method we have to keep V by F ratio constant. By rotor resistance control, we have torque directly proportional to slip by rotor resistance. This method is used for wound rotor motor only. By adding external variable resistance to rotor via slip ring, we can control the speed of motor. It can also use as starter. It is simple method. But there is resistance means heat means losses means less efficiency.
The three factors that determine the type of work a motor can produce are speed, torque, and horsepower. Speed is defined as how fast the motor performs its work. For example, a shaft can rotate slowly or quickly. The typical units of measurement for rotational motor speed are revolutions per minute or RPM. Work is defined as a force applied over a distance. In the case of flywheels, winches, and motors, the work is called torque. Torque is a special type of work that produces rotation. Torque occurs when a force acts on a radius. Typical units of measurement for torque are pound-foot. The torque illustrated here is equal to 1 pound-foot. Horsepower is defined as the rate at which work is accomplished. Years ago, before motors were invented, most work was accomplished manually. It was estimated that one horse could accomplish approximately 33,000 pound-foot of work per minute, and thus the term horsepower was born. In modern terms, horsepower is simply another unit of measurement for power and can be translated into watts, BTUs, joules, or any unit of power. Units that measure motor power are typically in horsepower or watts. You can manipulate the connection among speed, torque, and horsepower by understanding how they are related. The work accomplished here, the torque, is represented by the weight moving along the conveyor. If torque remains constant, speed and horsepower are proportional. As the speed, or RPM, increases, horsepower increases to maintain constant torque. If speed decreases, horsepower decreases to maintain constant torque. Let's say we wish to keep torque constant but want to increase the production of barrels. If the torque or number of barrels on the conveyor belt remains constant but speed increases, then the horsepower of the motor also increases. In other words, a more powerful motor is required to produce the same amount of torque more quickly. Similarly, the opposite is true. If we wish torque to remain constant and decrease speed, then the horsepower of the motor also decreases. If speed remains constant, then torque and horsepower are proportional. As the torque increases, horsepower also increases to maintain constant speed. As the torque decreases, horsepower also decreases to maintain constant RPM. Let's say we want production to increase, but the speed of the conveyor to remain constant. If torque increases, horsepower also increases to compensate. This means a more powerful motor is needed to produce more torque at the same speed. Similarly, the opposite is true. If we wish speed to remain constant and decrease torque, then horsepower also decreases. If horsepower remains constant, then speed and torque are inversely proportional. As the torque increases, speed decreases to maintain constant horsepower. As torque decreases, speed must increase to maintain constant horsepower. Let's say we want the horsepower of our motor to remain constant, but wish to increase the torque. If torque increases, the speed of the conveyor decreases, so that the horsepower required of the motor remains constant. Similarly, the opposite is true. If the torque decreases, the speed of the conveyor increases, and the horsepower generated by the motor remains constant.
Now let's see what are the different applications of induction motor. As I told that these are the most widely used machine in the industries and they have enormous applications. To name a few, I have mentioned here the few applications. Like for example, they are used in electric train engines. To drive the engines in the electric train, we use three-phase induction motor. Similarly, they can also be used for cooling fans that are used to cool large machines. So as you can see here the cooling fans are being used in case of a transformer, and these cooling fans are being run with the help of three-phase induction motor. There is another application there. They are used in chimneys at the power plants, and we know the function of chimneys. They are basically to exhaust or to remove the unwanted or poisonous gases and fumes from the power plants, and that is being also done with the help of induction motor. A very familiar application is in the case of printing machines. So here also the printing machines are being run with the help of three-phase induction motor. As well as they are used in rolling mills. They can also be used for large capacity exhaust fans. Now you can see here, these are the exhaust fans which is generally being used in industries to remove the unwanted gases, and here also induction motors are used. Then this you might have seen the cranes which are being used to lift equipments, and here also these cranes are being operated with the help of three-phase induction motor. Hoists, this we generally see near the construction areas, and these are also being operated by the three-phase induction motor. A very common example is the lifts or the elevators, which we often come across in apartments, in malls, and in many other places. So they are also being operated or run through the three-phase induction motors. So these are few applications which I have mentioned, but there are other n number of applications of three-phase induction motor.
We have classified these faults in 3 types, but these are further subdivided. Number 1, electrical faults. Number 2, mechanical faults. Number 3, environmental faults. Electrical faults, these faults are further subdivided into 7 types such as single-phasing fault. Single-phasing fault is occurred when any one phase of supply voltage is getting lost. Reverse phase sequencing fault. Reverse phase sequencing fault is occurred when any one phase of 3-phase voltage supply is reversed. Under or over supply voltages fault. This fault is occurred when supply voltages are under or over the specific limit. The limit of 3-phase AC supply voltages is 380 to 440 volts. So when supply voltages are crossed this limit, then motor could be burned or heat up. Overload fault. This fault is occurred when motor is overloaded. Means the higher load is connected at output side of motor. And due to this load motor could be heat up or excessive vibration. Earth fault. Earth fault is occurred when any one phase of supply voltages is connected to the housing of the motor, then motor is totally shorted. In this condition, when anyone will touch this motor, then he will feel the heavy shock. Beside this, the motor would take over current that could be dangerous for induction motor. Inter-turn short circuit fault. Inter-turn short circuit fault is the such type of fault when 2 turns of same phase or different phases are short circuits. Mechanical faults are such types of faults which are generally occurred in internal housing of 3-phase induction motor. These faults are further subdivided into 3 types such as broken rotor bar fault, environmental fault. In 3-phase induction motor, different faults could be occurred simultaneously, and in these faults, environmental fault is also so much important. Induction motor surrounding environment such as ambient temperature and moisture etc. affect on the performance of induction motor. These factors reduce the performance of induction motor. Beside this, the vibration in induction motor that could be due to any reason such as not properly installed also affect the performance of induction motor. So during the installation of 3-phase induction, this factor should be kept in mind.